And this area down in the southeast has the kind of rainfall that's equivalent to Tel Aviv annually. Where I live up here, near this island, we're about the same as the top of the Chemon, so about 1,500 millimeters. And then you get into the mountains and you get much wetter. So about 5 miles from where I live, the rainfall measured in the mountains can be up to about 6 meters a year. So you can have big gradients in quite small spaces. And again, with the temperatures, we've got a big range across the country. And this makes it very interesting from a sort of agricultural, environmental point of view. So this just shows some of the different environments from the mountain environments. This is about 5 miles from where I live. And then through to different types of environment, a lot of grazing. In Wales, particularly, grazing is the thing. About 80% of the land is grazed, so mostly by sheep. So about 5-6 years ago, we were asked by the Welsh government to develop a monitoring program because they wanted to develop the evidence base to understand how the environment was changing across the whole country. So they wanted this to be a platform that would go into the future, that would link with legacy data, but they could understand and inform their policy development through actual measurements and data, because they'd come to the conclusion that probably about 80% of the funding that they were providing for interventions was based on who shouted loudest rather than what the actual evidence was. So this is a program, these red and blue squares. We measure 1 kilometer squares, and we measure for all these different things. So from greenhouse gases, soils, the biodiversities, woodland, right across the board within these 1 kilometer squares. And then we use them to scale up across the country. So in the soil side of things, we measure a range of indicators. So just a basic suite, generally. We've got carbon and pH, density, nitrogen and phosphorus, just the basics. But this is what most people around the world who are doing monitoring are also measuring as well. So these are some of the results linked back to what's called the Countryside Survey in the UK. So in terms of the measurements for carbon and for pH, we go right back to 1978 when they started making measurements. And we have habitat land, which is the heaths and the bogs and the unimproved grasslands. We have improved land, which is improved grazing land, fertilized and arable agricultural land, and then the woodlands. And so we can see these different tracks of what's happening. On the improved land, there was a decline in carbon, which has kind of now stabilized in the arable land primarily. What's been interesting is that we've started to see this, what appears to be a decline in carbon in the uplands. We're not sure about this signal, and we need more data to confirm it, but it does appear that we have some kind of decline going on. And we think it's linked to acid grasslands, but we're not entirely sure. So in pH, we've seen the increase in pH over the last 30 to 40 years. This is about half a unit or more of pH nationally where we've had an increase. And this is primarily because of the stopping of acid rain. So this is a success in terms of policy intervention, where policy has been put in place to prevent sulfur deposition, which has decreased and the pH has rebounded. And so we start to get a picture of how the environment is changing. So as well as the program that we have of monitoring, we also have a modeling program that goes with this, and we're trying to develop a modeling platform that takes account of all these different aspects of the natural environment. So we link together different models to do with arable crops, forestry, what the farmers' actions are, climate change, and trying to generate this model platform that can be used to make predictive assessments. And so this has been used for the first time, looking at Brexit scenarios. So a lot of the Brexit planning over the last couple of years has been done using this modeling platform to look at different scenarios that might happen with Brexit. So I'm going to turn to some of the work on soil organisms, because we've been doing some work with DNA, and this is where the students have been pushing forward a lot of this work. So some of the nice things that have come out. So Paul George, one of the students, was looking at this idea of biodiversity, soil biodiversity. What do we mean by it, and what does it include? And he was very interested in soil animals, in the mesofauna. And so one of the findings that he put forward was that the animal richness and the mesofauna is impacted by the land use and its intensity. It's not affected by the soil properties, whilst the microbial richness is very much driven by the environmental properties and the soils across land uses. So we can't talk about soil biodiversity as one thing, as being driven by one thing. So it needs to be thought about in a bit more detail. Some of this work with the DNA analysis has been used in meta-analyses, and you can see here this big blue circle, that's us. So that's the data set that we managed to contribute. And in this piece of work, which was focused just on the microbial component, it was finding that the rarer taxa are more important in structuring the soil communities than are the abundant taxa. So what is in the tail is really important for determining what the community composition ends up looking like. And that was a piece of work that was led by Kelly Ramirez out of Wageningen. So some of the things that we've learned in Wales, what we do goes hand in hand with legislation, and legislation is really important. So that's been the foundation of driving the program forward. What you don't monitor, if you don't measure it, how do you manage it? It's very difficult. Everybody shouts a lot and nobody knows whether it's working or not. And we found that the modeling is really helping to manage expectations, to give understanding to policymakers. And so the program has built this link between the policymakers and the science in terms of trying to move things forward and helping with the management. And now even the farmers like it. So this is good. So now I'm going to switch a little bit onto some of our experimental work. Some of the studies that we've been doing, we do long-term studies. And one of the things that has been interesting me is different states of soil moisture. As many of you will know, I find soil moisture very interesting. So this is one of the areas where I've been working using long-term experiments. And we have this setup, which has been going now for over 20 years, where we have roofs. And I've come into this about halfway through. It was set up by ecologists to look at the impact of climate change. So both warming and drought, how that's likely to impact in the upland across Wales. And so they'd had problems with the soil moisture side of things. And they try to impose about a 1 degree rise in temperature. In reality, it's a little bit less than that, and about a 25% reduction in annual rainfall, which is something ultimately we may expect to see in Wales. We're already seeing some drying. So I did some work looking at starting with the hydraulic properties on the left side, the water retention. And this is the control treatment. This one is the drought. And what we could see is through time that the water retention curves had changed because the structure of the soil was changing. And this also affects the hydraulic conductivity. In the drought soils, we had higher hydraulic conductivity than we did in the control or the warming. So other changes that we see, things like the root biomass in the drought, the roots are going lower as we might expect on the search for water. So just to give you an impression of what the soils look like, these are thin upland mountain soils. We have about a 10 centimeter organic horizon that sits above about 20 to 30 centimeters of mineral soil. So this organic horizon, sitting on top of the mineral soil, what tends to happen is that the water builds up in this very porous layer. So we get perched water. But one of the things that they had noticed was when they started the experiment, this upper layer, they had been re-wetting in the winter, and it fills up to about 80% moisture because it's all organic. But we'd had several droughts, and this is marked by the Ds. Progressively, they're getting closer together. But after one of them, one of the things that they noticed was that the soil didn't re-wet anymore. And it's never reached that 80% again. It tends to be about 50 or 60%. And so they thought that, okay, there's something that we've done wrong, the sensors are malfunctioning, or there's something going on here that's a bit strange. So we went through all these things, and I decided that actually, no, it wasn't to do with that. And what I started to put it into was this framework of an alternative state, which is used a lot in ecology, and this idea that you have the system and you have some tipping point, and the system can move from one point to another if a threshold is passed. And you can think about this in terms of either a shift in variables or a shift in parameters. And this is what I think has been happening in our system, where you've got a structural change, the hydraulic properties have changed, and so this landscape that holds the ball has now changed and transformed, and so the ball rolls through the landscape and reaches a different equilibrium. And this was the idea that I put forward, that initially this could be a part of soil formation in the uplands in Wales, probably a natural part, but it affects the soil moisture dynamics. So you have an organic horizon over mineral soil, and over time you build up a sort of mineral organic impeding layer, and water starts to build up, but it has a low hydraulic conductivity and allows water to perch. But then when you start to get drought, then this material can crack. And as it cracks, it means that the water can't be held in the top anymore, the system drains, and so it alters the soil moisture. And so I sort of hypothesized that through time that you could start to see these changes in the moisture dynamics over sort of decadal time periods, where if you didn't have the cracks, you reach your stable state where you get 80% or so moisture, but then if you have the cracking, then it alters and changes to another stable state where the system is allowed to drain. And it could oscillate through these states as climate alters and changes. So I went looking for evidence to see if there was any other evidence that this might happen. And this was some data from the same kind of soils about 50 miles away from long-term monitoring in the 70s and the 80s. And we see the same thing happen. This is and particularly badly in a forest, where I think that the roots play an important role in really trying to desiccate and to crack the subsurface. But we see the change in moisture retention, and it's never recovered. So whereas in other systems, particularly in the deep dried out, it dried quite substantially, but then after about 6-7 years, it's bounced back and it goes back to normal. So it does appear that there is evidence that this kind of cycling may occur. It might shift completely and not come back, or it might cycle. So I couldn't have a talk and not talk about water balancing, because it's something that has interested me for a good long time. And every time I see Alan, we do have a bit of chat about this. I really like some of the work that Alan's done. It's very inspiring. And so hopefully I've made a little bit of contribution somewhere along the way. And recently we've taken things in a slightly different direction. First of all, I'm going to talk a little bit about some of the work that we did in Utah. So this is quite a long time ago, about 15 years ago. But it continues this idea of alternative states of soil moisture. And these are the Benjamin woodlands. They're out in Utah, in the US. And so we were working on sort of hydraulic properties of these soils. And one of the things that's very key in these soils is the water repellency. It's very clear. In these pictures you can see under the canopy of the trees, this is where you've got the effect of water repellency. As you get to the edge of the canopy and you get a complete wetting, the effects of water repellency are gone. And you see the uniform soil moisture. So in the top right here, you can see the sort of water repellent behavior that you get under the canopy, and here just a normal piston flow that you would see with the wetting matrix flow that we get in the intercanopy patches. And so some of the work that Scott and I did together, Scott Jones, who was also in Volcani, so I worked with Scott when I was in Utah, was just trying to model this. And we were able to just develop some modeling using Hydrus to show the feasibility of these patterns that you get if you have this kind of focusing due to the water repellency and then in the intercanopy patches, you just get the ordinary matrix flow. And so you can think about these as two different states of soil moisture. So some of the work that we've been doing more recently is to think about whether the soil water repellency is an emergent ecosystem response to try to mitigate stress in the environment. So I had the idea that that the development of water repellency could be linked to organisms, whether they're plants or bacteria or fungi, experiencing stress and responding to it. So in the case of plants, if they're subjected to drought, for instance, they might put out exudates, and this could help with the hydraulics, getting the water deeper into the profile, so there could be a feedback there. Again, if a system is too wet, it might be that the water repellency helps to keep it aerated for the roots. In the case of fungi with the hyphae, you lose less water, the system's more efficient. And in the case of bacteria, if you've got repellent biofilms, they can prevent desiccation, cell lysis, due to the sort of rapid re-wetting and the wetting dynamics in the system. So it kind of makes sense that biologically, the production of water repellency can be helpful when you're under stress. So we measured the water repellency for the soils across Wales. So Wales is not particularly the most stressed environment, but it gives us some idea of whether there might be some mileage in this idea. One of the key things that we found by measuring water repellency across the soils was that 92% of the soils across Wales are to some degree water repellent. Now, this was a bit surprising, which means that water repellency is the norm, it's not the exception. So the exception is generally in the arable soils, where we don't see water repellency. But in all the other environments, we see pretty high levels of repellency. So Fiona built this structured equation model with all the different data that we had, and incorporated both plant data and all the microbial data that we had from the DNA to try to understand how the whole system might link and operate. And when she took this kind of systems approach, indeed she found that in the first instance, if you have a wetter climate with a low nutrient status, which is stressed, then you do see increases in water repellency. And if you take out the microbial components, then again, the water repellency for the dry end is very much linked to precipitation and to drought. So it did seem that that stress is an important component of the water repellency story. It's not the entire story, but it also seems to be linked in with both the plant stress and the pH, which the pH is feeding into the organisms and impacting and affecting them and the nutrient status. So we started to come up with some general ideas about how this might function and operate. So if you have a sort of moist system, then as you're getting towards this wetter end, we expect that we will see more water repellency, because we have more stressed environments, tend to be more waterlogged, more nutrient deficient, which seems to be the case, and particularly more acidic. So we go from the neutral to the sort of more acidic side of things. But also we can see the reverse, where we go from these sort of moist systems through to the much drier systems, where we might go through desiccation, through cracking. We get the development of these kind of maintenance pools of soil moisture, going deeper into the soil. And we figure that, like I said, it could be advantageous to plants and organisms on both ends of the spectrum. And we did look at whether there was any evidence of a sort of shift in water repellency, whether it was whether you can see it along gradients. And pH is a kind of natural gradient for this. It's not that pH is necessarily driving it, but it's that pH also seems to be, is pretty good at describing a kind of stress gradient. So some of Ellen's measurements are here that we pulled together from the literature. And you see in the calcium kind of systems, you can get more water repellency. In the acidic systems, where you start to get aluminium coming out, again, you can get very high levels of water repellency. And in the literature, there tends to be a lot less data showing repellent soils that tend to be in this area around sort of 6 to 7, which you might think is the kind of less stressed kind of environment. Doesn't mean it doesn't exist, for sure you see repellency in this area, but you definitely see much more on either end. So it kind of leaves a question out there as to, the complexities of soil water repellency and whether there are biological feedbacks involved in that process. So there we go. That's given a sort of an overview. As you can see, there's a lot of monitoring that we're involved with, particularly on sort of decadal timescales of how change is occurring and trying to understand the changes that we are seeing, because both with land use and climate now, change is occurring pretty rapidly within our lifetime. And soils change. I mean, you still talk to people and they figure that soil is a completely unchanging medium. So even when I was in Wageningen and talking to some of the people there doing the modeling of soils, and they said, well, soils don't change. And I'm like, oh my goodness, guys, get with the program. So we need to move from this kind of static idea to one of the dynamics. And even in our own community, this is really important, understanding how change is impacting and what will happen. And so these kind of big monitoring platforms are really useful for developing and informing the evidence base for policy. And now in Europe, we have the Lucas monitoring program across Europe. I think they're going to be doing one for Africa as well. And so it's interesting to see how hopefully we'll start to see soil change evidence and data becoming more available in the literature, and understanding how the subsurface is altering, linked in with the plants and everything above ground. Okay, that's me. Oh, look at that. A few pictures to end on. So some of you will recognize yourselves.
Great, David. Thank you very much. Anyone want to ask any questions?
Yeah, show grid video. Let's see if we can. No, that wasn't what I was expecting.
I have a question.
No hard questions.
No, it's not a hard question. It was really nice presentation. It was kind of amazing to me to see the long-term change in the saturation of that soil. You didn't talk about what the chemical characteristics, the physical chemical characteristics of that soil are specifically compared to the peat soil that did return to its pre-drought levels of saturation. So I was wondering if you had any insights into that. What maybe could have driven that? Does it have to do with the physical chemical characteristics of the subs of the layer just below it before it gets to the mineral horizon?
Yeah, I mean, it's a really interesting system where you've got an organic layer. So pretty much like peat, about 10 centimeters of peat sitting on top of this mineral layer. That mineral layer is phenomenal. The things that are going on in that mineral layer, I see things that astound me. So for instance, we measured pH on a sort of bi-weekly basis for about 4 or 5 years. The pH can shift 2 to 3 units. I never seen anything like that. And it wasn't till I started to see some of the data coming out from John Chirova's group
Arizona.
in Arizona, where they'd been looking at changes in redox and how that affects the pH. And you can get massive shifts. And this is a redox system, you know, where we see these changes. So we are seeing phenomenal changes introduced by drought. And there must be the interlinkage between the chemistry, the biology. So the biology we know has changed. We've monitored that. So the ecologists have been looking at that. We know things like the routing has changed. One of the things that we observe, which I think is really important, is that the above ground canopy has hardly changed. So what you see above ground with the plants, it looks the same, all the pinpointing and what have you that's been done, the plants look absolutely the same. The soil has changed massively. And the structure has altered. We've lost carbon. So from the drought, we've lost quite a substantial amount of carbon from the system, which seems to have kind of mined out the soil. So, and we've seen a big shift over to a sort of more fungal based system in the drought. So there's a whole combination of different things that are going on. So we need sensors that measure pH. I'm absolutely convinced that this is something we really need to understand. Some of the things that are happening with the chemistry, and we need sensors to do it, to measure on timescales that we don't normally look at.
Have you published these results?
No.
Not yet.
No, we haven't. And nobody knows what to do with the pH. We thought we were going to get laughed out the place, that people would be like, no, that's not right. And since John Chirova's published on that, now we feel, I think, more confident. But we wanted to link it up with a model. And we've got a guy here called Jack Cosby who developed the MAGIC model. So he's really into pH. That's his big thing.
Yeah, right.
And he said, there's not a model on the planet that'll touch it. You just will not see that.
And you haven't determined the redox also, right? So you can't put that in. Is that?
Yeah. And it's so, you know, there's real sort of fresh ground there to be trodden. And I'm hoping that somebody picks it up and publishes it. But none of us feel confident enough to understand that chemistry, you know, the complexities of what's happening with it.
Yes, I could totally relate to not publishing something because you can't understand what the heck's going on. And the mineral soil, I guess it's non-buffered. Is that right? It must be silicious. It's not. I mean, it's not got a calcium carbonate, I guess.
Correct. Yeah. It's just trying to think. I think it's a chlorite. It's a shale. So it's mostly chlorite as the base sort of mineralogy.
Yeah. Wow, sounds really interesting.
Anyone else?
What do you think about the water repellency idea, this idea of stress in the system?
Yeah, I think that it's a good hypothesis to evaluate. I mean, it absolutely makes sense from the data, and maybe from the point of view of the organisms. I mean, after all, there must be a reason that they're doing this.
Yeah.
Unless. Yeah. Unless it's somehow connected to these so far not understood changes in, apparently permanent changes in the water, the ability of the soil to hold water. I mean, if you took the soil back to the laboratory without the underlying, you took those and then you just tried to saturate it, would you be able to force it to go back to 80%?
Oh yeah, no
You
problem.
would.
Yeah,
So
yeah.
it has to do with the structure of the column
Yeah,
below it.
yeah,
Okay, so it's definitely connected to the physical distribution and what's happening through the layers.
yeah,
Okay.
yeah, yeah. No, it's a physical phenomena that's gone on, because yes, it does re-wet. I mean, it does have water repellency, which is surprisingly fairly mild. I thought it'd be a lot more, but it's not driving things. So one of the ideas that I had, which, I mean, Uri, as a plant scientist, you might have some thoughts, is that for trees and plants in dry climates, particularly with these kind of pinyon juniper systems, one of the things that I had been thinking was that if you're in a stressed environment, you don't want to overgrow. So dumping carbon, if you can, is quite a good strategy to kind of get rid of it to prevent overgrowth. And one of the things I observed is that there's a lot more sap in areas where you were away from watercourses. So the further you were from a watercourse, and in the States they call them slicks, where you get these little streams. So the further away you are, the more sap production, the more resin you seem to see around the trees. And I thought, where they're stressed, maybe they dump. But these are also can produce water repellent compounds. And you also see more fungi under the trees as well. So I just wondered whether there was some link there with the trees of this kind of survival strategy, and that it kind of works out better for them because they create this hydrophobic system, which then gets water deeper into the soil and can kind of create a maintenance pool. But I'm not a plant physiologist, so.
Yeah, it's a difficult question, but the hydrophobicity of all kinds of mucilage and secretion around the roots is documented. I'm not sure how it is advantageous to the plant. I think it's a difficult question.
Yeah, I would like to ask a question.
Yeah.
So I'm an acarologist, so I'm interested in mites and what they feed on in the soil. So I work on predatory mites and they feed on nematodes. And you were speaking of mesofauna. So when I was wondering whether the people who did this monitoring, did they consider these organisms?
Yes.